the domain R, right? So this is going to be integrated over dr, okay. And of course this is going to give me, because this integration, when I attach this, is going to give me a Kronecker delta function, right, which removes the summation and leaves me with okay. So this is the Fourier analysis formula. Okay, so I can write down the corresponding formula for the creation operators as and these are dummy variables. So when I do a product, I need to use two of them in general. So now let's turn this. Let's represent the total number operator in terms of the wave function operators. And then you will see what the what the wave function operators mean physically. So we can write this is equal to the summation over I of two intervals. The B dagger comes first, so this is. Let me use the prime for the creation. Okay. Phi I. And then the B and the BI comes in, which is
no more prime.
There's no prime. Sorry, maybe this is
an arrow.
Yeah, that's an arrow.
Okay.
Yeah. Okay. So now we can combine the two intervals. How did I do this? Okay, so we're going to, because these things can be moved around freely, right? Because there's just functions, they're just numbers. Okay, so we have an integral over the prime and the unprime. And so prime. And these two are going to see each other. Okay. And we know that they commute with a. We're going to use this commutator relation now. Okay. So I'm going to turn this into this delta r minus r prime times the identity. And also minus R. Correct? Okay. So let's work with the first term. So when I work with the first term, I'm going to get now, one of these integrals is going to be removed by this direct delta function. So let me remove the prime integral. So we're left with dr, and this is y prime plus r. Right. I made a mistake somewhere. Oh no, this is not. Okay, I don't need to do this. So what I mean to do is I'm going to use this and this summation over here to produce a delta function. Okay. So I'm going to use the completeness relation in this set. And we just showed this, right? Okay. So I turn the summation inside of the integral, use this to create a delta function, and then use the delta function to remove one of these integrals. Right? So this ends up being dr by integral r. And if we need to be precise, we might add that the integration is over all of the space in which the wave functions are defined. So there's a total space of omega here, total integration. So, this kind of motivates us to think about this vector as some kind of a local density for the particles. So maybe interpret this as a rho of R, which is a local particle density. Right? Okay. So let's check this. Let's check this by defining some local, some operator, number operator that counts the number of particles in a specific region. So in a specific region, delta omega, okay, which is a subset of the whole space. Okay, so we're going to test if this really counts the particle within this region. And to check this, let's work with a simple one particle state. How do we build a one particle state at the position? How do I create a particle at the position R? Okay. I just start with this. Okay. I start with this thing. I take the adjoint of this, or the Hermitian conjugate of both sides, I get yn conjugate of R. This is equal to m by 7. Okay. So now, really this equation is independent of m. M can be anything, correct? Yeah. So I can say this is m times R, right, using direct notation. Oh, sorry, no, this is not. This is R, RM. Okay. Oh, wait. My bad. No, I was. This is M, R, right, and this is M by dagger R, 0, right? So now we conclude that because this works for any m, okay, so a state like this and this is a one particle state in a different sense. This is a so the wave function of this wave function operator is going to create a particle in some state, and that state depends on whichever you test it with, okay, which eigenbasis you test it with, okay, at the position R. So let's test this. Let's count the number of particles in this delta omega region for a state where we have created a particle at the position R prime. Okay. So this is n delta omega by dagger of 0. So now let's plug in this thing. And what we need to do is move this the annihilation operator, kind of a wave function annihilation operator, across this wave function creation operator. So do this by R. So moving this across, now we need the commutation relation. We use an identity operator R minus R prime, and then a minus sign and switch their order. Now this wave function operator directly sees the vacuum state. So this term can be thrown away. Right? So let's not forget the vacuum state here. Okay. So now we can use this integral, remove the integration over R. Okay, but it depends. It depends because we're not integrating over all of space here. So delta R minus R prime 0. Right? So now this integral is going to depend on whether R prime belongs to the space delta omega. Right? So this is equal to R prime 0. Belongs to here or else. Right. So now we have said that when I count the number of particles in a specific region for a one particle state created at R prime, then if R prime is within that region, I register 1. Right? Otherwise, I register 0. So this kind of makes sense. And it's very easy to generalize this to counting several particle states. Okay? But we're not going to do that. So this tells us that we didn't say how big this needs to be. So this can be made arbitrarily small. So this concept of a local particle density makes sense. Right? So the wave function operators, when their products are formed like this, they have a meaning of being the local particle density.
It should be a head on the roll. Head.
Oh, sorry, yeah. So maybe we take a break.
Take a break.
Are there any questions? No? No? Okay. So far we have seen how to work with one particle state. And really, so far this has just been a change of notation. The true advantage of this formalism haven't emerged. And it'll emerge when we consider multiple particle states, which we will do after the break. Okay. So maybe you can cover the polls on case on Thursday. I won't have time.
Okay.